Sushruta for NEET is now available on the Google Play Store. Try it out for free.
Last time we looked at waves and how to derive the speed of waves in a string, right? So there is a string, right? You have a string. What kind of wave do you have? You have a transverse wave, right? So now the same set of ideas are also seen. So this is where we were, right? So you have a wave which is caused by a, say, a tight string with a uniform tension T and with a mass per unit length of mu, right? So now in such a string, you give it a twang, so like that, right? So now the what happens to the speed of the wave, right? We derived this formula that the velocity, if you had a wave a sine kx minus omega t, its velocity is omega by k, where omega is 2 pi by t, right? And k has k is 2 pi by lambda, right? And 2 pi by t, or 2 pi f, right? And 2 pi by lambda. So when you write omega by k, you end up with f lambda. Okay, so omega by k is simply f lambda. Okay, so f lambda is v. Okay, the that is the fundamental formula that you must remember. Also, you must remember, from f lambda you can also derive omega by k, right? So 2 pi by lambda is like a wavelength number, right? And omega, as you know, is the frequency, is related to the frequency 2 pi f, right? So now, um, so wave number, right, and frequency, right? So v equals f lambda, and from that you have to remember how the two are, all of them are related, right? K equals 2 pi by lambda and omega equals 2 pi f, right? And therefore you end up with omega by k, right? And there is a simple way to show that the square root of t over mu, where mu is the mass per unit length, leads to v. V is, we already know, right? V is omega by k, right? But it's also square root of t over mu. So how do you derive that? See, the vertical force is this, right? The vertical force is the, you can derive it from using Taylor's rule, right? Taylor's theorem, right? You have the first derivative at point 2 equal to the first derivative at point 1 plus the second derivative times delta x, right? You leave out all the secondary terms, right? And you know that the if it is linear, you know that t at 2 minus t at 1 times u hat y hat equals 0 in the x direction. Therefore, you have, from this equation, you have you have the following theorem, right? So so what does that tell you? That gives you an idea as to how this can be derived, right? So so what do we do next, right? So the acceleration, right, is given by d square y by dt square, right? and the force is mass per unit length times delta x times the acceleration, ma, right? F equals ma. F is what? F we've shown is t times d square x by dt squared, right? So that's how this works. So y equals a sine kx minus omega t, and the force is mu times delta x, and the mass per unit length is mu, right? And therefore, relating these terms, force is equal to ma, and that leads to your formula T over mu equals v square. Okay, T over mu equals v square, where you can think of it as v square equals u square plus 2as, or v square equals as, right? Where a is the velocity, v is the acceleration, and s is the distance traveled, right? So, and the distance traveled here is delta x. So how soon does it go a particular distance? It goes a particular distance in this short period of time. All right. Therefore, you have v equals square root of t over mu. And v is equal to omega by k, right? Therefore, we end up with this formula. Okay, that's how this works. Okay, so the speed, now when it comes to sound, right? Sound is a little different. Sound is, what is sound? Sound is a longitudinal wave, right? Sound is a longitudinal wave. And so what does that mean? It means that you end up with a similar derivation, only this time you end up with the bulk modulus of the medium, which varies from medium to medium, divided by the rho, which is the density. Okay, so that's how this works. So the velocity is square root of b over rho. Okay, and so that's how we want to look at this. Okay, so when you look at bulk modulus, you use a similar formula, only this time you use pressure. Okay, pressure and the change per unit volume. So b is the bulk modulus and rho is the density. Okay, so greater the b, lower the rho. That's how you end up with square root of b over rho is equal to v. Okay, so keeping that in mind, at high frequency, b is taken as the adiabatic bulk modulus. So this is a similar derivation. Only thing, it happens in the context of a longitudinal way. They are very similar. The formula derivations are very similar, but it's how it is derived that matters. Okay. So now I'm going to continue, and that was just a refresher. So we are now going to look at um, how this works, right? So we looked at all this, right? Reflection of waves, standing waves, and string with both ends versus string with one end free, right? And so all this we have seen before, right? We saw how the when you apply two waves, right? And there is superposition, what happens? One wave is kx plus omega t, the other wave is kx plus omega t, and when you add the two, you end up with a pure standing wave, right? The pure standing wave is a sine omega t at any point, and so it goes up and down at any point, right? So you have it can be visualized by saying there are two waves, one coming in and the other going out towards the support, which are out of phase, right? Therefore they remain so more or less the displacement at zero remains zero at all times, and elsewhere it changes, right? So a sine kx minus omega t, right? Therefore, you end up with 2a sine kx cos omega t, which is a, at any point y, it is essentially, because the x is a constant, you just end up with the cos omega t. So at any point it will be a cos value, right? These two terms are going to cancel, right? So you have a sine kx minus omega t plus a sine kx plus omega t. So when you add these two, you just end up with these two terms. The amplitude will be twice as high, right? But it's going to have, in addition, also a sine term, which is proportional to x. So it's a standing wave which kind of moves around with time. Okay? So you can, if you take a cross section, any point it will be a cos t, right? Notice that even though the wave equation not of the form, no, this is due to the fact that does not represent a traveling wave. It is a stationary wave. It's a stationary wave which goes up and kind of goes up and down, right? And so that every point the string oscillates up and down harmonics, simple harmonically with a certain frequency, but also with an amplitude varying sinusoidally with location. And then we explained standing waves and the idea of what are called overtones, right? Or the various frequencies. So string tritide at both ends, you have harmonics, right? So you have uh, a sine kl equals 0. So when does a sine kl become 0? Becomes 0 when kl equals n pi. So when kl equals n pi, you end up with a that point will represent a zero of the wave, right? So what are all the points which represent zero of the wave? So you have kl equals n pi. So you have the velocity equals nv over 2l. kl equals n pi, right? And k is what? K is 2 pi f, right? Over omega over k is velocity, right? So you end up with uh, um, omega equals 2 pi f, and therefore you have 2 pi f by v will give you k, right? So when you have kl equals n pi, so you have 2 pi f divided by v equals n pi. So 2 pi f divided by v equals n pi. The pi is cancelled, therefore you have nv over 2l. The velocity can be rewritten as square root of t over mu, right? Nv over 2l, v is square root of t over mu, right? Therefore you have frequency equals n by 2l square root of t over mu. That's what you end up with. Okay, so n by 2l square root of t over mu. The distance between two nodes is the antinodes is lambda by 2. Okay, so now if you have kl, if you have a string fixed at one end, right? So when does this reach its maximum, right? So where are the maxima in that case, right? The maxima happen when sine kl equals 1, right? And sine kl equals 1, therefore you have n plus half pi. Therefore, you can see how this looks, right? So you end up with, instead of lambda n in the previous case was, what was the lambda, right? The frequency was n by 2l square root of t over mu, right? The distance between the two antinodes was lambda by 2, right? So here you have Vn equals 4L by 2n plus 1. Previously, we had 4L by 2n, right? Previously, we had 4L by 2n. Okay? So that is the main difference between the standing wave and the moving, between the one-ended wave versus the two-ended wave. Okay. So now, when do you have the one-ended and the two-ended wave, right? See, one thing that eventually you will understand, uh, or you should understand, is that when we speak, right, we have at our throat what is called a vocal cord, which vibrates. Okay. Then we change the frequency of what is heard by making a pipe. It is an open-ended pipe some of the time. Some of the time when I close my mouth, it becomes a closed-ended pipe, right? So I have a vibrator in my throat, and then I change the pipe is changed when you speak. So that's how we all speak. Okay. Um, so That's a important idea that I learned when I went to college. In fact, during my master's degree. Okay, so that is a key idea, and so today we are going to look at standing waves. Okay, so looking at standing waves in a where we introduce the phenomenon of beats. Okay, so when you have a pipe, you have standing waves. Okay, now if you have a pipe which is closed at one end or open at both ends, the pipe which is, see, now you still have the same thing as in the string. Okay, only that is transverse and this is longitudinal. That has T over mu, this has B over rho. Okay, now it is similar to standing displacement waves on a string. Okay, and so basically it's an air column, right? And so it's open at both ends, closed at one end, and open at the other. So those are the two cases, right? One is one side open pipe, other is a two-sided open pipe. The open at both ends resembles where the string is tied on both ends. Okay, closed at one end resembles the string where the string on the other side is moving up and down, right? So it is exactly the same derivation. Only thing it's B over rho, right? So here also you have various open-ended pipe. You have various variations of it. Okay, and therefore you have K equals N pi over L, right? And mu equals V over lambda. That you already know that, right? And therefore and lambda equals 2L over n in this case, and 2L over n plus 4L over 2n plus 1 in the case of the one-sided closed one. 4L by 2n plus 1, right? In this one, 2L over n. In that one, there's that extra half, right? So you keep that in mind, NV over 2L, N mu over, or NF over 2L, right? So each of those frequency, NV over 2L, each of those frequencies is called a harmonic, right? Now, V1 is the first harmonic, which is the lowest frequency. That is but then you also have these other frequencies that can occur in the line. Okay, so you have V1, V2, V3, and correspondingly, right? And the velocity, as you know, is root of B over rho. B is the bulk modulus and rho is the density, right? And the lambda in this case is 4L over 2n plus 1. In the previous case, it was 2L over n, as I previously discussed. Okay, so these are all the slight changes produces a different kind of answer for the frequency and the what are called the overtones. Okay, so the nth harmonic, the first harmonic is the lowest one, right? The first harmonic is where n equals 1, right? And so each of the harmonics will go up that much, first harmonic, second harmonic, third harmonic, etc. It will be going more and more and more, right? So the frequencies will keep going up with n, okay, and the wavelengths are therefore, it's the if you are interested in the wavelength, you have to use the n goes in the denominator. Wavelength is 1 over that, right? Notice that v is constant. Velocity at which all those waves travel is constant. It's only the wavelengths and the frequencies that change. So typically people remember the wavelength formulas based on whether it's an open pipe or a closed pipe, and then from that they derive the frequency and using v equals f lambda. And in this case, this letter mu, right? This is the velocity. This letter mu is the frequencies, right? In each case. So, and then they also have there is an end correction. Okay, now the end correction, the node at the open end of a pipe sometimes occurs at a distance slightly outside the open end at roughly 0.6 r units from where r is the radius of the pipe. If r is the radius of the pipe, 0.6 r outside is where it kind of closes. Okay, so that is what is called an end correction. So you can see here, right? So here it's from here to here, right? But then when you have an end correction, it goes a little bit outside 0.6 R units. The open end of the pipe happens there. So the effective length of an open-ended pipe becomes L plus 1.2 R, where R is the radius of the pipe. So you have a pipe like this, it has a radius. So you have you had 1.2 times R for an open-ended pipe, and for one side closed at one end, you have 0.6 R. Okay, so keep that in mind for the effect. Now, what is beats? It happens when two waves with slightly different frequencies superpose, right? That is, say if one wave has a eta 1 and the other wave has a eta 2, or f1 and f2. It's preferable to say f1 and f2, right? And so they are very, very close, right? So then you hear a beat, and the so that is a slow beat. Okay, you have two fast waves which are very, very close, then you hear this idea that of a beat. What is the frequency of that beat? It is the difference between the two frequencies. So v1 minus v2 will be the speed of the beat. Okay? So now people always talk of beats in the context of drums, so that is caused by the variation difference, the frequency, right? So when you have two superposing waves, you have this one, and then you have a w1 plus w2, and then you have a w1 minus w2 by 2. This one will give you the beat frequency. Okay, so this is the average, which is, if w and w2 are almost the same, then the common frequency will be, you know what it is, right? They are almost the same with the average of the two, right? But then the beat will be the based on the difference of the two frequencies. Therefore, the beat is kind of like that envelope, the frequency of the envelope, while the wave is the two waves have roughly the same frequency, but the beat will have that additional envelope frequency, which is the difference between the two. That is f beat equals f1 minus f2. So number of beats that are heard is equal to the absolute difference frequency of the two interacting waves. So here we get superposition of two waves, both showing beat phenomenon. Final resultant always shows beat phenomenon. So now the Doppler effect. Doppler effect is changing the frequency of a wave in relation to an observer who is moving relative to the wave source. So let's say there is a source producing a sound wave. Okay, and that has a particular frequency, right? You all know we hear in a certain range, between 4 and 7 thousand beats per second, somewhere there, right? The frequency of sound in air, 331 meters per second, right? 4K to 7K, somewhere there we can hear. Beyond that, also there is also, you heard of the dog whistle, they hear more, right? Now, so when you have this, right, what happens? Now, let's say a train is approaching a station. These are the most common questions with Doppler effect, right? The the frequency that is heard, because the emitter is moving, right, is changed by the person at the platform. It changes as as the train slows or speeds. Okay, so the received frequency is uh, changed by the ratio v minus v s, v by v minus vs, right? Notice that this is if uh, v by v minus vs, right? If vs is 0, right? The v is what? V is the speed of sound, right? Only one is moving in each of these cases. Okay, no, remember that. If both are stationary, which means that vs is um, 0, right? Then you have v over v. Now, but if the towards an observer, if someone is coming towards an observer with a velocity vs, right, the heard frequency goes up. I'm sure you've seen that, right? If if he's his his speed is At the speed of sound, V minus Vs goes to V minus Vs goes to 0. What happens when V minus Vs goes to 0? At the speed of sound, the receiver will hear almost a infinite frequency. Of course, you won't hear it, right? Because V emitted is a fixed value. It's the whistle of the train. It's a fixed value, right? Typically, that's what we assume. Now, as it approaches you, right, you find that you hear a different value, right, and you hear a higher speed, right. Now, if it is going away from you, it slows down because Vs is positive and V by V plus Vs is a fraction. So, based on whether it's coming towards you or whether it's going away from you, you hear differently. So this is where the source is moving. Where the destination is moving, when the observer is moving, let's say you're running from or you're driving a motorcycle and there's somebody part who's making the sound, right? So the emitted frequency is, so if you are moving towards the source, what you will hear will go up. If you're moving away from the source, right, in your motorcycle, it will go down. And what is the ratio? V plus B observer divided by V. V is the speed of sound. Okay, so this is the formula, and you will get a lot of questions relating to this. This is called Doppler effect. It is the change in the frequency as a result of either the source or the destination moving. So, and if you had both moving, you will then multiply it by twice. Okay, you have V plus V naught by V minus Vs, etc. Okay, so you must learn to solve these problems accordingly. So you can have both 1 and 2 happening. Okay? In which case V minus V naught, V plus V naught by V minus V naught, etc. So, or you can use a relative effect to determine the effect of the frequency. Okay, so so when the frequency changes, the observer, why does this happen? It is because the observer experiences a changed distance, right? What is the effective distance? That changes. Therefore, you end up with these differences in the speed. So if you have both the source and destination moving, you have V plus minus V naught divided by V plus or minus Vs. Remember, notice that when the observer is moving towards the source, you have a plus. When the source is moving away from the observer, you have a plus. Okay, so who is moving matters. In one case it is plus, the other case it is minus. Okay, so keep that in mind, and but remember that it is the relative to each other. Two people are moving. One is moving with the velocity VO observer, other is moving the velocity VS source, and corresponding the frequency that is heard is changed. Okay, so source moving towards a stationary wall and receiving its own sound back, that is called an echo, right? So you will hear a second frequency V plus Vs by V minus Vs times the frequency. So the frequency that you hear back, right, is V plus Vs by V minus Vs, right? And that is the effect of what you hear back. Okay, so so there is it is somewhat similar to two people moving. Only thing, two people are not moving. Okay, so keep that in mind. This is similar to when two people are moving, but then you have only a Vs. You don't have a VVO. You see, so the V double prime, the final frequency received by the source, is V plus Vs by V minus Vs times. Okay, so think of it this way, right? Think of it as relatively there is a Vs and there's a V naught. If you're running, but the wall is not running, right? It is similar. It is same as you going this way and the wall coming that way, right? So you have a net effect that of the frequency that you hear, which would be V plus Vs by V minus Vs. It is actually in some ways very similar to this formula. Only thing, the VO and Vs are the same. In one case you have a plus, the other case you have a minus. So when you are going the other way, if you're moving away from the wall, also you will have this, but you will have V minus Vs by V plus Yes. Okay, so it will be exactly similar. So this is Doppler effect. Please try out a lot of problems involving Doppler effect. This is a very um, um, well, they will always, when they come to pipes, they will ask you about these overtones, various frequencies, and then they will ask you about Doppler effect and the frequency that is heard. Okay, train, when it's the whistle of the train, all these questions will come. You're standing in the platform, etc., etc., etc. Okay, so keep that in mind. And with that, I'm going to close today's chapter. Going to let you all go little early today, but then please solve a lot of problems and download our app and continue learning. Okay, so with that, I'm going to stop sharing, and we will meet again next week.